In image sampling and interpretation, if you want to make your image small, right? Say a big image is given to you, you want to reduce the size. Reducing the size of the image is called as subsampling. When you want to subsample, you want to throw away, say, every row and every column. If you remove every row and every column, every alternate row and every alternate column, then you'll make your image size half. From this, if you remove every alternate row and every alternate column, then your image will become 1/4. From this, if you remove every alternate row and every alternate column, your image will become 1/8. Right? Now, if I now zoom this to this size, to the size of this, and if I zoom this to the size of this is how it appears. I mean, there's a lot of information which is lost. The cheek of a person, I mean, it's going inside and inside here. I mean, that means you're losing every alternate row and column, right? Hence, it's appearing like that. But that's not a good way to deal with that, because when you do image subsampling like that, just throwing away your alternate rows and columns, you get into an issue called as aliasing. Look at this. Okay, here you have that aliasing effect. Here also towards the top, you see the aliasing effect. Here also there is aliasing effect because the image subsampling has not been done properly. So if image subsampling has to be done properly, you have to follow something called as Nyquist rate or Shannon's sampling theorem. What does this theorem say? This theorem says that whatever sample size you want to pick up, that sample size should be greater than or equal to twice of the maximum frequency. What does that mean, right? You have a doubt. So let me clarify it using this example. Say this is the image that you have. This is the image that you have without those circles, of course. If you move from this frequency to this frequency, I mean, if you move from black to white, this will give you the maximum frequency change, right? Yeah. But if you move from this point to this point, is anything changing there? No. Here, is anything changing? No. So you look at all the frequency changes and take the maximum frequency change. Here, how many maximum frequency changes are there from black to white? Only one. There is only one maximum frequency change. So your sampling rate should be greater than or equal to 2 times of this maximum frequency change. Maximum frequency change is only one frequency change here. So your sampling rate should be greater than or equal to 2 times of 1. So it should be greater than or equal to 2. So let's see whether the first image is a good sample or not. If I pick 4 pixels from here and 4 pixels from here, is it a good sampling? Yes, because you have 1, 2, 3, 4, 5, 6, 7, 8, right? If you have these 8, you can track the movement from black to white. So this is a good sampling. Is this a good sampling? You have chosen 1 pixel here and another here. Yeah, okay. Because your sampling frequency should be greater than or equal to 2 times of max frequency change. But max frequency change happens to be 1 because black to white. So this is also good sampling. And how about this? No, this is a bad sampling because here you haven't chosen anything. Right? Here you have 1, but here you haven't chosen anything. So you have not chosen. And is this a bad sampling? Yes, because you have chosen here, but here you haven't chosen 1. Here also you haven't chosen 1. Here also you haven't chosen anything. So this is a bad sampling. So Shannon Nyquist rate says that the samples that you choose should be greater than or equal to 2 times of maximum frequency. Otherwise, you run into this aliasing issue. In order to, okay, let me show you another. What issue should I show? Okay. Blades rotating. Yeah. That's the illusion that we are getting. It's moving at a rapid pace, right? Let me show you this one. Reverse rotating. Have you ever seen whenever a car goes at a rapid pace, right? You get an illusion as if the wheels are rotating in the reverse direction.
Yeah, we can see it at the back.
Back wheel, it appears as if it's rotating in this way, right? These are illusions which are caused because of wrong sampling rate. Wrong sampling rate. So Nyquist sampling rate is very important for video capturing as well. Otherwise, you'll get a different illusion, as if the blades of the helicopter are not moving, and that kind of illusion is what you get. Okay. So why is that happening? That's happening because the video that you're capturing is not capturing proper frames per second. What is a video? Video is nothing but frame of images or frames of images captured at a rapid pace. So here you have frame 0, then you have frame 1. In frame 1 it's moving like that. Frame 2, frame 3 and frame 4. Right? In each frame you see that this particular dot is moving in the clockwise direction. But what if you're first capturing frame 0 and you're not capturing these 3 frames and you're capturing frame 4 directly? Then it appears as if from here this is happening. So it appears illusion as if it's the counterclockwise, right? So it depends on the shutter, camera shutter, basically. And also human eye. When you look at a fan rotating, if you try to rotate your eyes at a rapid pace, you'll be able to see the wings, right? Otherwise, it gives you an illusion as if it's rotating at a rapid pace. So all these are examples of your Nyquist sampling rate. To counter that, to follow Nyquist sampling rate, this is the solution which is proposed. When you have a big image and when you want to reduce that, one way to reduce is throw away every alternate row and column and then blur the image using Gaussian filter. Then throw away all the alternate rows and columns and blur the image. So this is how it will appear. If you apply a Gaussian filter, throw away every alternate row and column, blur it. Throw away every alternate column, blur it. Throw away every alternate column, blur it. This is how it will appear. As opposed to not blurring. If you do not blur, this is how it will appear. If you blur, this is how it will appear. I mean, if you consider these two, difference is quite evident. And when you deal with text, this is what happens. If you have this as your text, if you're performing directly subsampling, look at the amount of information that is lost. However, when you smoothen the image and then when you subsample, look at what you're getting. Is this better or this better? Obviously this. So you have to smoothen the image and then subsample. So simple. You have an image, blur it, subsample. Blur, subsample, blur, subsample. When you keep doing that, you will find or you'll get something called as Gaussian pyramid. Right? Pyramid of your images. What is the advantage of this? It's used in image detection. Have you observed this that on Facebook when you upload an image of you along with your friends, it tags your friend's name. For example, if Wilfred is my friend on Facebook, assume, then Wilfred might have uploaded a lot of images of his, and maybe his cover page has a photo which is taken from a close-up, a selfie, assume. But the photo that I've uploaded of me along with probably Wilfred and Shah and Jack might be from a far-off place. That means in the image, Wilfred's face is like that, Shah Jack and me, right? Assume. But Wilfred's actual Facebook images are all close-up images. But this is far off. Then how does the mapping happen? Mapping happens based on Gaussian pyramid. So what happens is behind the scenes, you take all these images, make a smaller version, smaller version, smaller version, and have all the sizes of images ready. Then when you do the mapping, it quickly maps this size with the corresponding. It will be easier for object recognition. This is called as object recognition problem. Basically, this is how you solve it. These are all the same thing. For satellite also, you have all the varied sizes that you have, and then you do the mapping, image processing. That's about downsampling or subsampling. When you want to upsample your image, that means you're given a small image, you want to increase it. You want to make it bigger. Then what do you do? You repeat each row and column. If you want to make it 10 times bigger, you repeat each row and each column 10 times. That is called as nearest neighbor interpolation. How does it work behind the scenes? Suppose you have data for all these pixels. Now you want to add more pixels. So what do? You choose a pixel value. Nearest neighbor says, if this pixel value is closer to this, then assign this value to this. If the pixel value is closer to this, then assign this value here. If the pixel value is closer to this, assign this value. If the pixel value is closer to this, assign this value. That's called as interpolation or upsampling your images. Yeah, if you have a small image, you want to make it big. There will be some blur. Okay,